Good day, everybody. My name's Steve Wally, and I'm the governing board chair for the Confidential Computing Consortium. Can I have that the second slide, please? So the consortium was formed in October of 2019, and it's a nonprofit under the Linux Foundation umbrella. We focus on open source license projects, securing data in use and accelerating the adoption of confidential computing through open collaboration. May I have the next slide, please? And as you can see, our members are a broad collection of cloud service providers, chip manufacturers, and independent software companies. We continue to pick up new members. Just in the last 2 weeks, we've picked up Western Digital has joined and Cisco has joined, as well as Applied Blockchain. So we're continuing to grow the membership. Today, we're talking about one of our projects. Graphene is one of the early projects that joined the consortium. I'd like to introduce you to Don Porter and Mona Vij, two of the founders and maintainers of the project, to tell you more about the project. And with that, I will turn it over.
Thanks a lot, Stephen, for the introduction. Before I jump into the talk, I'm Mona Vij from Intel Labs, and I've been part of the Graphene project from the beginning, from the time when the idea started with a conversation with Don Porter at a conference. So Don, do you want to quickly introduce yourself?
Hi, I'm Don Porter. As Mona says, I'm an associate professor at the University of University of North Carolina at Chapel Hill, and one of the founding members of Graphene.
All right. So let's just first start with the confidential compute definition from the consortium. So confidential compute is the protection of data in use for performing computations in a hardware-based TE. So while there are other techniques for protection in data in use for computing on encrypted data like homomorphic encryption or multi-party computation, but when we refer to confidential computing, we are mainly referring to computations in a hardware-based TE. So let's also now take a look at what a trusted execution environment is in this context, because there's several definitions that are floating out there. So it's any environment that provides you some level of protection for data confidentiality as well as code and data integrity. And a hardware-based TE typically provides these properties by mapping the TE to a secure portion of memory and implements access control for denying any access to the code and data inside the TE from outside accesses. And in majority of cases, hardware also provides an interface for attesting to a third party that you are indeed running in a TE, and so they can actually provision secrets to the TE. And most major hardware vendors support TEs today. We have Intel SGX and upcoming TDX. AMD has several generations of ASSCV and an ARM trust zone. But today's talk, we will focus on the most awesome TE, Intel SGX. So let's just start with, before we look at what SGX is, let's just look at what the attack surface of an application is. So in a typical application, the attack surface includes your application, as well as the whole system software, operating system, VMM. With Intel SGX, this attack surface is changed. And it is reduced just to this little area in the application called enclave and the hardware. SGX is implemented as a set of ISA extensions, and a typical programming model for SGX splits the application into an untrusted component and a trusted enclave. And after this split, hardware will ensure that neither the untrusted part of the application or the system software can access this anything that's running inside the TE. And also specifically in SGX, the untrusted application actually builds the trusted enclave's initial state with a very well-defined entry points. And SGX provides this interface for proving to the third party that you are indeed running in a TE. And that basically includes the initial memory fingerprint of the application as well as well-defined entry points. So while splitting an application into an untrusted application and the trusted enclave ensures a small TCB and strong security guarantees. It also increases the effort to build and maintain such a split. So in the untrusted cloud and edge deployments, there's a strong desire to not split the application, but rather shield the application from its secrets from the system software. And this basically results in a design where the entire application is running inside the enclave. And but running your application inside a TE is just one small piece of the puzzle. For building this end-to-end secure solutions, developers really want a push button approach. You not only you need a framework that can build the TE with well-defined entry points, you also need frameworks that can automatically provide TE primitives like attestation and secret provisioning. And this is where Graphene comes into picture. So Graphene actually supports this lift and shift paradigm for unmodified applications for confidential computing with Intel SGX. So let me quickly introduce the Graphene project before we go into deep dive.
Hey, Mona, let me just pause you for 1 second.
Sure.
I'm Jesse Schrader, part of the Confidential Computing Consortium's Outreach Committee. And just for the audience here, there is a Q&A button, and you can submit questions, and we'll keep track of those along the way and provide them to our speakers along the way, or we can save Q&A for the end as well. So we want this to be as interactive as possible. So even though you can't interrupt with your voice, you can submit those questions and we'll make sure we get them to our presenters. So go ahead, Mona.
All right, thanks, Jesse. Yeah, so let's just look at the project summary. So first of all, Graphene project is not officially part of CCC quite yet. While we have received the technical acceptance, we are still waiting for legal review for trademark and naming. So Graphene is a library OS designed to run unmodified Linux applications on other platforms. While our current focus is on SGX, the project is intended to be much broader and can support other architectures as well as operating systems. It's a community maintained open source project under LGPL license. And the project has well-defined testing and validation criteria. We have CI/CD running on Jenkins, and we also have a clearly defined governance structure for project development and maintenance. Graphene is also already deployed for POC deployments and integrates well with Azure Kubernetes services. And while Graphene has matured a lot over the years, it's not quite production ready yet, but we are working towards a production ready release in Q2 21. So it's coming up soon. And like I said, Graphene is actually a very fast growing project, and we have a growing maintainer community. We already have contributions from several individuals, universities, big and small companies. Several startups have joined the maintainer community. And they're contributing both in form of the code as well as bringing their use case requirements in helping with the overall direction of the project. And we also already have a growing set of well-tested applications that are already running on Graphene. These includes AI/ML frameworks, databases, web servers, and several languages that we already support. So at this point, let me hand over to Don to give you a little bit history of the Graphene project as well as architecture overview.
Thank you, Mona. Okay, so here we have on this slide sort of an overview of what a typical Graphene instance looks like. So again, at the top, so first of all, this box on the left-hand side of the slide represents the initial version of Graphene where we ran in a process. And maybe let me pause and give a little history first that, so Graphene started in, God help me, in 2011, 10 years ago, when I was a fresh PhD and new faculty member. And, we wanted to start up, sort of a big implementation project. And the underlying research hypothesis we were interested at the time didn't have anything to do with trusted execution or confidential computing. We were initially interested in questions around portability. And there was a structural observation underlying this that if you look at an OS kernel, there's sort of a lot of code at the system call interface that creates a fairly large and complicated API that ultimately sort of funnels down to a small number of primitives like give me some memory, let me do some IO, et cetera. And then it sort of fans back out again to a lot of hardware specific code. And the underlying question was whether we could do user kernel separation sort of at that narrow pinch point in the structure of the kernel and make that the interface. And if we make that interface simple and easy to implement, then we can lead to more portable applications. So that was the overarching idea or goal behind the experiment. So in the picture now, we can show a process address space. This could also be a VM or any other address space. And at the top of the picture, you see unmodified applications as well as supporting libraries that are taken, don't need to be recompiled, nothing, just binary as is, that run, ultimately programmed against the 325 some odd Linux APIs. Those Linux APIs, instead of being implemented through traditional system calls, are implemented by a dynamically linked library that's slotted in underneath a lightly patched libc. We currently implement about half of those system calls, and those system calls are then implemented on top of a narrower ABI of about 50 calls. We call this a library OS because it's in some sense, all the application supporting code of an OS bundled up in a library. You may have also heard the term unikernel used fairly synonymously with this notion in other contexts. One small distinction is that Graphene is again programmed against these ABIs I'll talk about in a minute, whereas unikernels are often programmed against bare metal or virtual metal. Finally, this 50 ABIs that Graphene is implemented against are exposed by what's called a platform adaptation layer, or PAL. These are again intended to be easy to implement simple functions like give me a page of memory in my virtual address space, give me a thread of execution, or let me send packets on a socket. The hope being that these are interfaces that any sensible OS or VMM should hopefully be able to support. This is ultimately then funneled down to 50 Linux system calls. And again, this is sort of what this looks like without SGX. And we published this result in 2014 at Eurosys. So around that same time, as Mona mentioned, Intel was announcing SGX, and we had a fortuitous chat at a conference about sort of both the anticipated need for lift and shift to run unmodified code in SGX, the fact that code doesn't just work out of the box on SGX, that some work needs to be done, if nothing else, to defend the code from the untrusted OS. And this seemed like a real opportunity to kind of make the point. This ultimately led to, sorry, had a lag in advancing the slide, to this collaboration and a subsequent paper on porting Graphene to SGX that appeared at ATC in 2017. So now we can see how we demonstrated this sort of overall portability point using Graphene SGX. So instead of having the process address space, we can do something very similar inside the enclave, that the enclave's address space, again, can have the unmodified application and shared libraries and Graphene underneath it. The main change that we needed to make was to implement an SGX specific PAL, first of all, as well as a shielding layer. So again, the PAL here encapsulates some of the host-specific idioms of how you get traps out to the OS. In this case, instead of doing system calls, we do enclave O calls or outgoing calls to the untrusted runtime, which then relays calls as needed to the untrusted OS here at the bottom of the slide. The other thing that we added is a shielding layer inside the enclave at the boundary with the untrusted code here at the bottom of the enclave box. And this is, again, this is intended to essentially sanity check the results of responses you get from an untrusted runtime environment to make sure that they're sensible and to detect misbehavior. Finally, the Graphene plus the SGX PAL amounts to around 50,000 lines of code, which is not nothing, but is several orders of magnitude smaller than Linux, and frankly, several orders of magnitude smaller than glibc, and compared to most production quality application code. So I want to unpack the shielding layer a little bit. And the goal here is that one addition to Graphene on SGX that we needed to make was defending against an untrusted OS. The original Graphene design was actually concerned with sandboxing untrusted code. And so now we need to do shielding in the other direction. And so, a few things that I want to highlight here that Graphene provides for the application. First of all, any files that you map into your address space or read, we have the ability to check them against a known good hash, so we can check the integrity of what's brought into your TEE. For files that you want to protect, we can do transparent file encryption using standard file system interfaces like open, read, write, and close. And this can be application transparent. One feature of Graphene's design is that everything is pretty much implemented in user space, including things like fork and multi-process abstractions like System 5 IPC. We also support live migration from one machine to another, and this is all implemented through encrypted messages between enclaves, right? So if you want to fork, we actually bundle up your entire address space using encrypted messages and send it over to another enclave to reconstruct your address space. Pipes, messages, and signals are also encrypted, and we have some additional system call specific checks for other PAL interfaces. The one exception to things that we don't do on the application's behalf is that in our experience, network communication is so ubiquitously encrypted with SSL and TLS in practice that we don't transparently re-encrypt your network communication a second time, just because I don't think it just adds overhead without buying much. So that would be sort of one caveat to be aware of, that, if you bring up Telnet inside of Graphene, it's still going to send your password in plain text. One of the things that's the main burden on an application deployment that Graphene requires is what's called a manifest file that basically describes the requirements of your computation. So we have an example manifest for Redis, and it's in a TOML format. We recently changed the format to be a little more user-friendly. And I'll walk through a few of the example fields that you might need to specify. So one is you need to specify the path to the binary that you want to load. You may also specify environment variables. This is probably a good idea. You can also specify what the view of the file system should look like. So you can list multiple directories on the host that you want to expose as sort of chroot style mount points, as well as where inside of Graphene's view this file should live. So in this example, we take the file /graphene/runtime and make that appear to the application as if it's in /lib. You also need to specify some SGX specific parameters, at least if you're running on SGX, like the maximum enclave size and number of threads. And finally, you can specify trusted files, which means in this nomenclature, trusted means that it's integrity checked, but in plain text. So for instance, if you're using libc.so, when we build your image, we'll get a hash of that file on your system and make sure that at runtime, you get a libc that matches the same hash, or we'll reject it. Some other useful SGX features that Graphene supports. So first of all, we have support for SGX attestation, both the EPID and DCAP models. So this is for demonstrating to either a local or remote party that you're running the computation you think you are. As I mentioned on the previous slide, we support protected files, which means that we can, first of all, and I guess I should say at 3 levels. So one is that we just allow you to read things. You can specify that a file is either untrusted, which means you can read it and write it in plain text. You can specify that it's trusted, which means that it's integrity checked with plain text, or protected, which means that it's transparently encrypted and decrypted. For performance, we have adopted asynchronous or exitless system calls. As I mentioned previously, we support multi-process applications. And what this means is that if you want to run 3 collaborating processes or applications, multiple Graphene instances can work together to provide the illusion to the application that they're running on a single shared Linux kernel. And this is again coordinated through message passing across, or encrypted message passing across the enclaves. Finally, we support Docker integration. So as you may have noticed on the manifest slide, a lot of the things that we had to say around what you need to specify is not terribly different from writing a Docker file, for instance. And so, observing that rough isomorphism, we've also developed tools that can take a Docker image and convert that into a Graphene image for easier deployment. Okay, finally, I'd like to do a slightly deeper dive into the remote attestation part. And the way that I find it helpful to think about this is that there's 3 levels of attestation that we support. At the most basic level, one of the features of SGX is the ability to check that an enclave is running the code that you expect. And we support this with multiple backends, again, including DCAP and EPID, as well as we expose a pseudo file system called dev attestation, where you can roll your own attestation support on top of it. Using that basic building block, and again, using this basic building block, we can then establish secure channels among enclaves using the RA-TLS library. And finally, on top of all that, we can also support secret provisioning. So a common model is to establish a trusted execution environment, attest that it's in the state you want, and then you give it some secret that lets it either decrypt inputs and start working, or otherwise sort of unlocks the computation to get started. And we have support for this as well with additional libraries. So with that, I believe it's time to hand the baton back to Mona.
All right, thanks, Don. So let me give you a little bit deep dive into how we do the container integration. So as many of you may already be aware, containers have become the de facto deployment model for the cloud. And it's mainly because of the small memory footprint, fast startup time. So it was very clear to us that providing integration with containers is going to be instrumental for deployment of secure workloads with Graphene. It's hard to teach people about this new libOS abstraction. So our goal was to provide an interface to create Docker images to basically automatically secure the existing Docker container images with Graphene. And as Don mentioned earlier, while you don't have to modify your application or binary at all, you do have to provide a manifest, because manifest is what really defines the security posture. It clearly calls out what's protected, what network interfaces you can talk on, what files you can access, and it could be a bit of a burden for complex applications. So with Docker containers, we also wanted to see if we can bring in unmodified Docker containers and generate these manifests automatically. So just at a high level, we actually have this tool called Graphene Shielded Containers, which effectively takes your unmodified Docker image. Optionally, you can give it a manifest that specify how much enclave size you need, how many threads you want in an enclave. And even if you don't specify it in Graphene, GSC can default to some good known values. And effectively, this tool takes this image and actually creates a graphenized Docker image. And this basic image will include the application, the Graphene runtime, and an automatically generated manifest, right? So the interesting thing is we are able to generate this manifest based on the observation that container already is packaged to bring all the dependencies that an application has. So we basically overestimate and pull in all the files and libraries specified in the image and allow them in the manifest. And but after you create this image, all SGX applications also need to be signed. So GSC also just takes this graphenized Docker image and creates a signed application within this graphenized image. And then this image is handed over to the Docker runtime. As far as the Docker runtime is concerned, it's still running a Docker image, but as part of the startup, Graphene would create an enclave and host the whole runtime and the application inside a Docker container. So let's just discuss what does it mean now to create this end-to-end solution with all these different pieces that we have talked about. So let's imagine a use case deployment where you want to run an object detection service in an untrusted cloud environment. And the goal is to protect both the model IP as well as the user private data that you're running the inference on. So in this case, for the deployment, you can start with a vanilla Docker image and then give it to Graphene, and Graphene will be, or GSC, and GSC will wrap this image automatically into the Graphene runtime. And before transferring control to the application, Graphene actually uses the attestation interfaces that Don described, generates an attestation over the RATLS secure channel, sends it to a verifier, and gets the key provisioned. And at that point, it actually transfers the control to the application. An application runs as it would. These encrypted files are brought in and they're automatically decrypted by Graphene. Application just sees the clear data, generates the output that's also again automatically encrypted with Graphene and put it back on the store. So this basically shows how you can build this end-to-end, say, secure machine learning inferencing pipeline using Graphene out of the box. And if you really wanted to experiment with this tutorial, on our GitHub, there is the tutorial is there. You can actually play with the code and see how it works. So yeah, just getting close to wrapping this up. As we said earlier, Graphene is very actively evolving. The initial SGX port was open sourced in 2017, but the community really formed when in December 29, when Golem and ITL joined hands with us. And that's when we put together this project governance structure, and since then we've been growing very actively and getting contributions from other parties. We did the first major release in September 2019, but in the last 1.5 years, just some stats here. You can see we have over 1,000 files that changed. That pretty much includes all the files in Graphene. And interestingly, we have inserted as much code as we have deleted, because just as part of cleanup and refactoring, a lot of the effort has been around just making the research code into production worthy code. So thankfully our TCB size hasn't changed. The code size more or less remains the same, and over 1,000 commits from 34 authors in last less than 2 years. Yeah. And most of the memory management, threading, processing, and signal code has been reworked. And it's just great to see how far we have come from that initial prototype. So our immediate goal, as I said earlier, is to get this production ready release out in Q2 21. And as part of that, we will improve the tooling and the documentation. And there are lots of other infrastructure pieces appearing, like confidential service meshes for confidential computing. And we are talking about integrating with these other infrastructure pieces to ease the deployment in the cloud as well as edge. And we continue to grow supported runtimes and workloads as we stabilize Graphene. Couple other things that we are looking at is extending the secure communication with the accelerators. There's lots of uh, mm, emerging demand for that. And today, Graphene doesn't really support any other devices other than network and file system. And we will also explore addition of future TE backends, because Graphene architecture is very modular. We could develop a different PAL for a different architecture. So yes, we on behalf of the Graphene community, we invite you to join our community. Bring any type of contributions. You can contribute code or issues. Dawn will take fruit baskets as well. And then, yeah, just really try your unmodified Docker workloads with Graphene. And we want to hear from you. You can, good or bad, share your experiences of using Graphene with us. And with that, I leave you with a couple of links here to our GitHub as well as the project page. Thank
Great.
you.
Thanks, Mona. Thanks, Dawn. Thanks for moving through that stuff. We've gotten quite a few questions from the audience. Thanks, audience, for submitting those. So I want to pitch some of those to you guys, and Dawn or Mona, you guys can decide who wants to step in on each. First one, you mentioned migration, you mentioned forking processes, these capabilities. What about, what does Graphene have for supporting distributed computing? Thinking about, attestation, key coordination between TEEs. How are you set up there?
Dawn, do you want? I can answer.
Well,
Yeah.
yeah. Why don't you take that one, Mona? I'll take the next one.
Yeah. So yeah. If I don't know what you mean by the distributed support in general. Like I said, we automatically support attestation. So if you do need a backend attestation framework, but Graphene does provide a sample attestation framework for you too, because you need a verifier. And we have some sample code out there where you can build your own verifier, but there are certain guidelines you have to follow to get certificates for your machines that are running those enclaves. And like I said, we actually do link to other backends. For example, we already link with the Azure attestation backend. And there is some exploration we are also doing, which we call it the mutual attestation. Can two Graphene enclaves mutually attest each other? And that's somewhat work in progress. I don't know if that answers the question, but.
Okay, yeah, no, I thank you, and I think obviously getting involved a little bit more with the project, there'd be opportunities to dive deeper into attestation. I know you guys have a lot more content on a lot of the detailed functions and processes and how they work. How about another question? What about how does Graphene handle the capacity limits of enclaves? We know that historically SGX enclaves have been pretty small memory regions that could host. We know that's changing, that we're going to have much larger enclaves coming in the Ice Lake hardware that's due very soon. Can you talk about how Graphene manages that?
Sure. So we certainly make some effort to just be lean and mean and not waste memory if we can help it internally, or to minimize the footprint we add to already scarce resources. And in SGX1 by default, we kind of have to deal with some of these limits and let the driver do some swapping. We're actively working on supporting the enclave dynamic memory management feature that SGX version 2 has, which will help in terms of giving the application a little more control or ability to manage its own memory, as well as to get rid of things that are not in the current working set size. other research, such as the Elios project from Technion, has also built sort of user level swapping and shown a lot of good support for, or a lot of good results supporting that. We don't do that transparently in Graphene, but that can also help quite a bit if your application has enough of a runtime that it can store things in an untrusted swap and do application level encryption. But like a lot of things in this world, this is, you know, we're also learning a lot as we go.
So I guess just to add to what Don just said, with the upcoming Intel Ice Lake platforms, we are going to have really large EPC. And so that EPC size limitation actually in many ways goes away. And Graphene can support gigabyte, large EPC enclaves, and we are running quite a few workloads in that scenario. But in the end, we just rely on the driver to do the paging. We have no restriction from Graphene's perspective. There's no restriction on the size of the enclave. Even on today's platforms, you can create really large enclaves, and driver will handle the paging for you. Yeah.
Great, great. Okay. Another question is about just how an educational institution or a lab can get involved. I think, you know, we've got some reference links up here. I'm pretty sure that through the Confidential Computing Consortium and the project progress there, I think any organization can be part of that. Members of the CCC get a vote in some of this stuff, but I think anybody can attend sessions, anybody can leverage the materials. What other ways can labs or institutions get involved with Graphene?
So certainly, you know, for a research lab at a university, certainly, you know, feel free to contact me or, you know, or the team as a whole. But, you know, if I had a project that I wanted to port into running on Graphene, you know, I might start by just trying to run it and see what happens. And, you know, and there are some support resources, both documentation and a issue tracker or mailing list, and see. For things that aren't sort of easy to fix or that require more substantial work, or if you want to look at you know, more efficient or optimal things that you could do with something more customized, you know, we can have that conversation out of band. But otherwise, in general, like our hope is that a lot of things will work more or less out of the box at this point. And in general, though, like for anybody who wants to get involved, like send us issues, send us patches, or you know, bring up things that you'd like help coding up, and we'd be happy to talk to you about it.
Yeah, and the mailing list actually link is not up on the screen, but if you go to the website, there's a mailing list address. You can feel free to reach out to us. We also meet every once a week mostly with the maintainer group, but you are welcome to join that as well, and just ask us for the information on that.
Yeah, right. I would go ahead.
Go ahead.
I was just going to say that before, you know, if you have the notion of doing something substantial with Graphene that might involve serious changes you'd like to upstream, you know, certainly running that by the maintainers, you know, sort of at design time or in advance would help smooth out that process. But, you know, yeah. Jesse.
And keep in mind that an educational institution or nonprofit lab, you know, anybody in that nonprofit category can actually become a Confidential Computing Consortium associate member, and that's free. So if an organization that's nonprofit is interested, you can actually become part of the CCC and really get involved in the project through that mechanism, in addition, obviously, to the project stuff that's out on GitHub, et cetera. Okay, good. Continuing on, what about compatibility with development languages? I guess we're kind of wondering, you know, what's here now, what's coming?
So yeah, if you saw, we can already support a number of different languages as long as your runtime runs on Linux, like, because we said we can support unmodified Linux applications. We did run into some challenges, for example, with Java or Go, but that was to do with just the sheer size of enclave. And you're right, someone earlier pointed out with 128 or 256 megabyte EPC, it just runs really, really slow. So we have support for Java and Go coming up very soon. And the goal is really to be able to run pretty much any language on top of Graphene.
Yeah, I mean,
Okay.
just as sort of one example for a managed, like many JVM applications, as we discovered, the first thing they do as part of initialization is allocate a gigabyte worth of 0 pages. And if that's part of your launch and there's no demand paging in SGX1 and you've got about 93 megabytes to work with, it's going to take a minute to zero out and hash all those pages.
Yeah. Luckily, that's not going to be an issue for much longer.
Exactly.
Yeah.
So that's exactly the point, that with the large EPC and the dynamic memory EDMM support, those problems will go away. Yeah.
Okay. All right, thanks. Now, you guys talked a fair amount about how graphene is implemented. Can you give some examples of some promising areas where you're seeing graphene being used? I'm thinking of types of usages.
Yeah, actually, there are quite a few usages in flight. The example I used for secure machine learning, I think that's a big use case for protecting model IP and data, and I believe there are few startups who are working in that space. The other big use cases is around federated learning, where you want to be able to compute, do training or do learning exercise on these remote sites in untrusted locations. And again, graphene is being used for that use case as well. And there are a few other projects that are in flight that are very close to productization. And some of them, they just need the big EPC and the production readiness of graphene. Actually, I've also seen some databases use cases as well. Uh,
Okay, yeah. So I think I'm hearing from you that while a lot of folks are still kind of in the development phase, the proof of concept phase with this, and they're waiting for those larger enclave sizes to be available before they can really go to productization. So maybe there's not a ton of public announcements yet on things in graphene, but sounds like there's quite a few real world engagements that are already involved in this process.
Exactly. And one other area I forgot to mention is again the VNFs, virtual in the 5G space. We are running a lot of the virtual functions in the cloud, and the security of those is quite important. And we have some projects again in flight. And like Jesse, you said, not quite there yet, but quite a few of them are in flight, and hopefully we'll see them appear later this year.
Okay, great. Well, I want to be conscious of time. I know it was our goal to get out of here at 45 minutes. You guys have done great at managing that. Any kind of final thoughts, maybe from each of you? Final call to action or anything before we close?
Yeah, I will just say that it's very exciting to be here today, and the project has come a long way, and especially for if anyone who looked at graphene a long time ago, it's just completely a different project today. It's just so we definitely want you to go try it out and let us know your experiences.
Yeah, I concur. I think that I've built a lot of research prototypes in my day, and many of them are sitting on GitHub collecting dust. And it's nice. It's nice to see one that turns out to be useful for some people, and I'd like to keep that going.
Yeah,
And
great.
so thanks.
Great. Thanks, Mona. Thanks, Don, for taking the time to put this together. And I agree, it's exciting to see how far graphene has come and to see where it's heading. And yeah, just thanks everybody for attending today. And consider this just the beginning. There's a lot more information out there. The Confidential Computing Consortium is open and welcoming additional participants and contributors. So looking forward to talking to all of you more. Thanks a lot, everybody.
Thank you.